Right. So this is the first video for chapter 9, which is regression, which is a huge topic in statistics. So why don't you pause, copy this down, and I'll start chunnering. All right. So in regression, what we're going to try and do is we're going to seek to model a relationship with something linear. Okay. Now we're going to see by the end of the chapter that we can put a real big tweak on that idea of linear, but still we're going to try and model relationships between two or more variables with some kind of linear relationship. Okay. All right. So the first idea is something you've seen in Math 313, covariance. All right. So if we've got two variables, x and y, this is section 9.1, by the way. So if we got two variables, x and y, we can define the covariance of x and y to be the expected value of this product, x minus its mean times y minus its mean. And what that's trying to get at is some kind of sense of what kind of a slope exists if there are a line fitting x's and y's together, okay? And let's see why. So let's say I have this scatter plot. Horizontal is x's, vertical is the y's, and I put in where the mean of y is and the mean of x. And these black dots are my data points. And I've created quadrants, 1, 2, 3, and 4. And what you note is that most of the data points appear to be in quadrants 1 and quadrants 3. And that there's this vague line with a positive slope that you could think of as a line of best fit that would run through the data somewhat, right? All right, and so let's see how covariance is capturing that idea of a positive slope. So in quadrant 1, the x values are greater than the mean of x, and the y values are greater than the mean of y. So xi minus mu x is positive, so is that, so the product's positive. Now in quadrant 3, xi is less than mu of x, so xi minus mu of x is negative. And the yi's in quadrant 3 are less than mu of y, so this is negative as well. So the product of those two negatives is also positive. And so this data, this product throughout all the data tends to be positive. So you'd expect its value to be positive as well. And that's what the covariance is capturing. Okay, so let's move on to the second panel. And I think I maybe should stop using green. So maybe we just need to get a little closer. I'm not sure if that helps or not. All right. All right, so why don't you pause, copy, and press play. All right, so for the rest of this video, I'm just going to show you a few interesting facts about covariance. So here's the first one. If I took the covariance of x with itself, by definition, that would be x minus mu of x times x minus mu of x's expected value. And if you note, that's the exact same definition as the variance of x. So the variance of x is the same as the covariance of x with itself. Okay? And then the second observation is the way we're going to tend to calculate covariance is using this formula right here. So the covariance of x and y is the expected value of x times y minus the mean of x times the mean of y. So we're not going to tend to use the definition of covariance to actually calculate it. We're going to tend to use this formula here. So we should probably prove it. So if I want to figure out the covariance of x and y, by definition, it's the expected value of x minus mu of x times y minus mu of y. And the first step of my proof is just to FOIL that product out. So I get x, y, I get x times mu y times mu x, and mu x, mu y. Okay. Now, expected values can happily rip apart addition and subtraction, right? So I'm going to split it there, there, and there, all right? And also remember that for expected values, if you've got a constant like mu of y times a variable, you can drag that mu of y out in front of the expected value part. So there's my expected value of x, y, drag the mu of y out from next to expected value x, drag the mu of x out and left the expected value y behind. And then the expected value of mu of x times mu of y, those are just two constants. So the expected value of that product is just that product, okay? All right, next up, expected value of x, well, that's just mu of x. Expected value of y, that's just mu of y. So it looks, sorry, that's just mu of y. So it looks like these two guys are just mu y times mu x in either order. And I've got two negative copies of it. So there it is. There it is. And so if I've got -2 copies of mu x, mu y, and one positive copy of mu x, mu y, altogether I have one negative copy of mu x, mu y, and the e of x, y comes along for the ride. Okay, so that's the formula we're going to tend to use. Let's take it for a spin now. Let's determine the covariance of x and y, given that x and y are in the relationship defined by this joint PDF. 3/2 x squared plus y squared, x and y 0 to 1. Excuse me. So what I need to calculate is three things: expected value of x, y, the mean of x, the mean of y. Okay. All right. So first, I'm going to go for the mean of x. I'm going to find the marginal PDF with respect to x. So I'm going to take the joint PDF and integrate the y out of it. All right. So integrate with respect to y's bounds, do some calculus, and I get that for my marginal PDF of x. And now I can go for the expected value of x. So I'm going to take x times the marginal of x and integrate over the bounds of x, do some calculus, and I get 5/8. Then I'm going to do the expected value of y. Okay, the exact same way. I'm going to get the marginal and the expected value of y. Please note, x squared and y squared, everything about x's and y's are symmetric here. So whatever I had in terms of x's, I'm going to have in terms of y here. So I'm going to get the same expected value for y as I got for the expected value of x, since this joint PDF was completely symmetric, right? All right, so I've got mu of x, I've got mu of y. Now I'm after the expected value of x, y. So I'm going to take the joint PDF, multiply it by x, y, and double integrate over x's and over y's. I do a bunch of calculus, and I get 3/8. And so then I can bring it all together. The covariance of x and y, there's e of x, y minus mu of x, mu of y, and I get -1/64. All right, so that means there's a negative slope relating x and y's together, and it's pretty close to 0, which we're going to find out means that there's not much of a linear relationship there, right? It's kind of a horizontal line is the line of best fit, which could be saying that there's not much of a relationship between x and y. Okay, 1.5 more panels to go. So why don't you pause, copy, and then play. All right. So one nice consequence of that shortcut we showed in the last panel for calculating covariance of x and y is that it makes clear that if x and y happen to be independent, then their covariance is always 0, right? So, and the reason why is that e x times y from the shortcut, if their x and y are independent, the expected value of x times y is the expected value of x times the expected value of y, and that's exactly mu of x times mu of y. So that'll make that covariance calculation 0 right off the bat. Now, unfortunately, if you learn that your covariance is 0, it doesn't guarantee you that x and y are independent. So here's a counterexample. So here's how I'm going to define my variable x. It only takes on 3 values, -1, 0, 1, with those probabilities. And then I'm going to define y to be very dependent on x. Y is going to be x squared, all right? And if you like, that means for y, let's call it g of y. Y only takes on the values 0 and 1. Y is 0 when x was 0, that was half the time. Y is 1 when x was -1 or +1, so that's half the time as well. Okay, all right. So x and y are definitely not independent because y was based on x, right? You can easily calculate the expected value of x. That's -1 times 1/4 plus 0 times 1/2 plus 1 times 1/4, and you get 0, which, by the way, you'd also get with the expected value of x cubed, because x cubed would have -1, 0, and 1 as its table, just like x does. All right, so let's calculate the covariance between x and y, which is x squared. The shortcut says it's the expected value of x times the x squared minus the expected value of x times the expected value of x squared. That's the mu of x and the mu of x squared. Now, the expected value of x cubed, we just said was 0. The expected value of x, we just said was 0. So that whole value is 0. So we get the covariance of x and y is equal to 0, but x and y are most definitely not independent. So just to recap that, if x and y are independent, you know the covariance is 0. But if you find the covariance of 2 variables is 0, it doesn't mean the 2 variables are independent of each other. Okay. All right. Okay. Well, another nice fact about covariance is if I have a bunch of random variables, x sub I added together and a bunch of random variables, y sub j added together, and I'd like the covariance of the sum of the x's with the sum of the y's, then it's like I can just drag those two summations way out in front and do the covariance of each x with each y, and then add them all together, okay? All right, little hand wavy proof here. I'm just gonna grab two x's added together and three y's summed together and calculate the covariance. So by definition of covariance, that's the expected value of this sum minus the mean of that sum times the y's added together minus their mean, okay? That's the definition of covariance. Expected value of x minus mu of x times y minus mu of y. X is played by x1 plus x2. Y is played by y1 plus y2 plus y3. Okay. All right, well, expected value of x, expected value of x1 and x2. The expected value can push through that sum, and I get the mu of x1 and the mu of x2 with the negative signs. Same deal with the y's. I can group x1 minus mu of x1. Oh, sorry. So then I'm going to group x1 with its mean. So x1 minus mu of x1, x2 minus mu of x2, y1 minus mu of y1, y2 minus mu of y2, y3 minus mu of y3. Great. So I'm just going to multiply x1 minus mu of x1, y1 minus mu of y1, plus x1 minus mu of x1 times y2 minus mu of y2, right there, plus this guy times the third one. And then I can run the x2s through the y's as well. And I'll have a big, long string here, all within the expected value. Expected value loves addition. So it's just going to have all those additions are summed over all the i's and all the j's of that product. And that expected value is the definition of the covariance of xi and yj. Okay? So covariance loves addition, basically, is what we're saying. Okay? All right, and then last panel, why don't you pause, copy, and then play. All right, so in the previous panel, we proved a big, long sum result. So one of the consequences of that sum result that we'll use a lot is if I look at the variance of the sum of x, random variable x with random variable y, we know that the variance of x, the variance of a variable is the same as the covariance of the variable with itself. So the variance of x plus y is the same as the covariance of x plus y with x plus y. Okay? That was from earlier in the video. And now this, the theorem we just did in the previous panel tells me how I can split sums in both spots there. I can do the covariance of x and x plus the covariance of x and y plus the covariance of y and x plus the covariance of y and y. And then the covariance of x and y and the covariance of y and x, that's the same exact thing. So that's two copies of the covariance of x and y. And I know the covariance of x with itself is just the variance of x. And the covariance of y with itself is just the variance of y. So I get down to this result here. Okay. So the variance of x plus y is the variance of x plus the variance of y plus twice the covariance. So please note, that's like FOILing. X plus y squared is x squared plus 2xy plus y squared. Well, the x, y is being played by covariance, and the x squared and the y squared are being played by variance. And please also know, I'll skip down to here, if you happen to know that x and y are independent here, then we already showed that the covariance of x and y is equal to 0. So we just get this nice result, right? We can generalize this variance of the sum idea to be the variance of as many things as we like. And so we get all the variance of each variables plus 2 times the covariances all added together. Okay, this will not come up much. We usually just tend to do it with 2 guys.